We'll talk later. It's nice to see you, sir.
Unbelievable. This computer just shut down for no reason at all. It was like, doot, doot, doot. I'm like, and I swore and took the Lord's name in vain for several times. And then I went down because my power went off. But Tara's doing fine down there. So the power didn't go off. So I'm not exactly sure what's happening. But yeah, so there's that. So why? Because why not? They just like things blink out. Like the whole computer just shut down. It's not that it just got kicked out. Like the whole thing just shut down. Viruses. CJ sent me something. CJ sent me a weird link. I just opened it up, and now my computer has a virus.
I tried, guys.
All right. Well, who knows what that was about, but I'm going to persist beyond, and we'll get back into assumptions because I know you all were worried about like, oh no, maybe we won't get to keep talking about assumptions, and that's to ruin my day. I didn't sort of get that sort of figured out. Okay, so I think before I was so rudely interrupted by technology, there we go. Okay. Assumptions of our statistical tests. Make sure that's off. All right. Reason we're worried about assumptions, okay, is our entire framework is based on the assumption that we know what these distributions look like, okay? And if the distribution, the sampling distribution of our test statistic isn't what we think it is, then all of a sudden those probability values that we're associated with, the p-values and sort of the whole fail to reject stuff is way off, right? So as long as we're playing by the rules, we know what happens. As soon as we start to deviate off of those, things start to fall apart, okay? So again, I think, in my mind, so an easy way to think about this sort of sports analogy. So Riley, so you went through and you were thrower in track and field, is that right?
Mm-hmm.
Okay, so what did you do? You shot, discus, what
Discus and javelin.
Discus and javelin. Okay, so within college athletics, right? If you're throwing disc, right? You're assuming everybody's using the same weight disc. Everybody's using the same weight disc. Disc is all made from the same materials. Everybody has the same amount of room to sort of go through and do stuff, right? And if that's the case, if we're playing by the rules, then if you throw farther than Erica or Natalie or Robert or so on and so forth, right? Then we know who's better, who's throwing stronger, and we're feeling comfortable with that, right? But let's say now all of a sudden you go and now Erica's got a different weight disc, or Robert gets like a 30-yard run at it, and so he's got a sort of a different thing that sort of doesn't, all of a sudden, if we start doing that now, if Robert throws farther than you, we don't know anything about who throws better or not because we're violated all the rules, right? Same thing with our tests. If we have all of our assumptions met, we know the distribution of this test statistic, and we can start to apply specific probability values. But as soon as we start to violate that stuff, now all of a sudden we've got a test statistic that has a distribution that we don't understand. And if we don't understand it and don't know and can't predict it, we can't assign probability values. And now all of a sudden, like we can't draw reasonable inferences from these data. Okay. So it's important to go through, and we'll spend a lot of time. And this is really where most of your time in data analysis ends up being spent, is trying to figure out like what's going on with my data. Is it meeting my assumptions? I'm always going to have violations. What do those violations mean in terms of inference? How do they start to impact sort of the conclusions I can draw from the data? Okay, so from a single sample t-test, we're formal assumptions. We're assuming that our outcome variable is continuous. Okay, now we often don't have continuous scales. We'll treat ordinal scales with 5 or more values as continuous. We've got some data that suggests that this is probably good enough in terms of continuous, but know that technically what we should have is a true continuous scale where sort of values can take on any sort of value, but as long as it's ordinal with 5 or more people, will generally give you a pass on that. We're also assuming that our observations are independent, right? So if I'm measuring some outcome, what I need to make sure of is that Allie's scores are Allie's scores and not dependent on Robert's scores and not dependent on Rachel's scores, that all of these data points all of our observations were obtained independently from one another. This is determined by methodology, right? And this is where if you start to get into nested types of data, right, where I'm looking at sort of your scores on, let's say I'm looking at your scores on some outcome, but then I'm comparing those to someone else's cohort, sort of second years and third years. Well, there's sort of dependency because you have stuff that your scores are likely more related to any random score in someone from another cohort just because of shared experiences. So wanting to be careful if we identify potential non-independence, sort of making sure that we're taking note of that and realizing that would be a violation. Okay. And then we're assuming that the distribution of sample means for the population is normal. Okay. Under what conditions, Natalie, does my distribution of sample means start to become normal?
When the sample size increases.
Okay, as my sample size gets large, and sort of what else?
I'm not sure.
Someone help her out with what's the other thing? Rachel, you know this because you've answered it before. What's the other situation in which my distribution of sample means starts to become normal very quickly?
Is it if the original population
Yeah.
is normal?
If whatever I'm measuring in the population has a normal distribution, right? So if I'm looking at, if my outcome measure is height, right? Even with small samples, the distribution of sample means is going to become normal pretty quickly just because height has a normal distribution in the population, okay? So technically, with our means-based tests, we're not actually concerned technically with our observed distribution of our outcome because the test doesn't require that our data be normal. It requires that the sampling distribution of the data are normal. And so as long as we have, and so there's a Bono article that talks about, if I've got sample sizes of at least 30 or larger, my tests tend to be pretty robust to things so long as my distributions aren't weird and crazy and sort of completely out of bounds, right? But as long as I have samples of about 30-ish, my observed data can be actually pretty non-normal with our means-based tests, and we're going to assume that they're pretty robust as long as it's not getting too out of bounds, right? So we still want to go through and look at our distributions, but wanting to remember that technically our assumption pertains to the distribution of sample means and not the actual observed distribution, okay? And this is good because this gives us a little bit more flexibility with things. Okay. Informal assumptions, we're assuming that our data don't contain outliers or extreme values. Partially dependent on sample size. If I have a sample size of 30 and someone who's way out of bounds with stuff, that's going to start to have a much bigger impact than if I have a sample of 250 and I've got some people on the margins. This is something that we'll go through and do continuously throughout the semester, going through and screening these data and start to say, okay, is this problematic? Is it not? Because that's the thing, right? We want to go through and say, all right, this is what's going on in our data, and then make a determination. Is this something that I need to be worried about? Or is this something that my analyses will be probably fairly robust to? Okay, because we don't want to ignore our assumptions, but we can get too crazy the other way and start identifying that anything that's not perfectly normal will start like transforming and doing weird stuff when it's not necessary, and it overly complicates things. So wanting to be careful there. Okay. And then remember, always in the background, we have these auxiliary hypotheses. These are part of statistical theory that we ignore, but all of these tests assume that our sample is representative, that it's normally randomly sampled, that we don't have violations of distributions. So that's what we're talking about here. that our hypotheses were generated prior to the evaluation of the data, that we didn't make up our hypotheses after we've looked at stuff, that we've correctly specified models, that we've included all variables, that our measures are valid and collected without error. Like, these are all things that are technically part of sort of what makes all this work. We just ignore it and pretend it's not there to our hazard, because then we start to make unwarranted assumptions, right? Now, we're never going to get a sample or a study that sort of hits all these criteria, but we should be aware that we are violating these things and thinking about potential consequences. Because if we don't know what our actual distribution of our test statistic is, right? And then that starts to sort of negatively impact our inference. Okay. So, whoops. So, for our example, what we're going to do is we've got a data set, your single samples T set that you should have open right now. Okay. And what we've got is the inventory of interpersonal problems. 32 is a self-report measure intended to assess domains of interpersonal difficulty. Total scores range from 0 to 128 with mean equal 25 and a representative validation sample of 800 adults. Okay, and then we've got sort of what our sort of characteristics of our representative validation sample here. Okay. Researchers are interested in the effect of stress exposure on global interpersonal functioning. Responses to the IAP 32 are obtained from university undergraduates, a large sample of 405 individuals reporting distress associated with exposure to prior trauma. Okay. And then we've got the characteristics of our sample here. Okay. So what we're going to do with this, we're going to go through, we're going to state the null hypothesis, we're going to state the null and alternative in using symbols, we're going to calculate confidence intervals, we're going to provide an index of the absolute magnitude of the difference in the sample relative to the normal population. What are we talking about here? We're talking about the absolute magnitude of a difference. What are we calculating? An effect size.
Yeah.
There we go. I beat you to the punch, right? So calculating an effect size. We're going to go through and calculate. Then we're going to run a hypothesis test. We're going to run S values. We're going to calculate Bayes factor. And then we're going to summarize our conclusions, bring it all home. Okay. So a lot of different things to sort of go through and do. But what we'll do is we'll start with these single sample T and kind of work from there. Okay. So let's, before we start jumping into this stuff, what we want to do is go through and do an initial screening of the data. Okay. So if you've got your handout that has your single sample screening here. All right. And then let's move you out of the way here. And then we'll have our data set right here. Okay. People comfortable with this? All right. So what we need to do, so what we want to do in terms of our assumptions is we need to make sure that our outcome variable is continuous, our observations are independent. I'm not worried about independence of observations. I had people coming in. I'm not worried that some people's IAP scores are related to other IAP scores. And then what I'm going to do is sort of really what I'm going to focus on is take a look at what this IAP score or what this IAP variable looks like in terms of the distribution to see kind of where it's at with stuff. Then we're going to go through and look for some outliers and things like that. So here I have my single sample test. Here in SPSS, I've got at the top here all my variables. Okay. If I go down to variable view, click this, I see here's my participant number. I've got participant sex, age, ethnicity, some different scales. What I'm interested in here is my IIP total. Okay. So that's the variable I'm interested in first and for this example. So what I'm going to do first is I'm going to go to my IAP total because that's the variable I'm interested in. And if I go through and I click on that and then I right click, and I go sort ascending, that'll go through and it's going to sort my data in order. Okay. Now, why I'm doing this is I want to see if I go through and I sort, what SPSS is going to do is it's going to take any value or any case that doesn't have a value, and it's going to sort of shift those cases with missing values up to the top. Okay. And so what I want to do is I want to say, Ari, if I have a bunch of cases, what do I have? I've got 70 cases. I've got 70 cases with no data in it. Can I use those cases?
No.
Nope. Those are cases where I don't have my outcome, so I can't sort of use those for anything, right? So I can't use those, so I'm just going to go ahead and get rid of these. Always first, before I change anything, I'm going to go File, Save As, and wherever I have this, I'm going to call this a scrap file or a working file or something like that, so you always want to be working with sort of a working file or a scrap file or something like that, because otherwise what's going to happen is you're going to change data, and then you need to be like, oh, whoops, I made a mistake. I need that data back, but you can't get it back because you've already changed you never want to be working with your sort of formal set. You always want to be working with a copy, right? So I'm going to go through, and then probably what I'm going to do is I'm going to pull up some sort of document and says, what's this? Okay. Something different. All right. Working with the document, and I'm going to say 70 cases. Missing IIP 32 total, just so I know, hey, I've gone through and I've got a bunch of missing values in this set. Okay, so what I'm going to do after I document that is I'm going to say, all right, and I'm just going to go through and I'm going to delete that. Okay, so now what I've got is a set that has complete data here. Okay. People follow me there? Okay. So I've gone through and I've gotten rid of all the data, all the cases that don't have data, right? So now what I want to do is I want to go through and remember my main concern or my main criteria or assumption here with my single sample test is looking at the distribution of my outcome variable. Okay. So what I'm going to do is I'm going to go to Analyze, Descriptives, and I'm going to go down through and I'm just going to select, double click IIP 32 total score. Okay. And what I'm going to do then is I'm going to go to Options, and I'm going to ask for skew and kurtosis, right? Because remember we had sort of talked about skew and kurtosis as giving us information about the distribution, and I'm going to hit Continue. And then I'm going to also go through and I'm going to hit Save Standardized Values as Variables. What this is going to do is it's going to create a new variable that just gives me z-scores for each case. Okay, so I'm going to go through and hit that. And then what I'm going to do is I'm going to hit Paste. Okay, so if you hit Paste, what this is going to do, who here has worked in SPSS with syntax files before? Okay, Brittany's worked with syntax files. Anybody else worked with syntax files at all? Rachel, a little bit. Allie, okay. What we want to do with our syntax files is this gives us a record. This gives you a record of what you've gone through and what you've done, because I'll tell you what's going to happen. You're going to go through and you're going to run things and you're going to come back to it a week, 3 weeks, months later, and you go back, what did I do? Right? Your syntax file gives you a record, allows you to go back through and redo stuff that you've done so that you're not having to run through stuff in the pull down menu over and over again. And eventually, when you get good, when you're running the same types of analyses over and over again, you can just work from the syntax file because it's going to be faster and easier when you've got certain programs that you're putting together. Okay. So in my syntax file, I'm going to go through and anything, if I go through and I put double asterisks, You got to have a space there. I'm going to say looking at distribution of IP32 total. Okay. You can write little notes to yourself so that you know what you're doing. Anything that you start off with a double asterisk is going to be, that's just a note. It's not going to run anything. Okay. And then what I can do is if I go through and I highlight this, I can go through and hit this little green arrow. I can run this. And what's going to pop up then is my output window here. Okay. So if I'm taking a look at my output, what am I, Riley, what are you seeing here in this output?
The descriptive statistics of the total score?
Yeah, some descriptive statistics. Is there anything that's looking strange on that descriptive statistics? Does anybody see anything that gives them pause or might cause concern?
I mean, I don't know if this is right, but the standard deviation is kind of big.
Standard deviation is pretty big. Yeah. What's the scale of this measure? All right, I've got scores ranging from 0 to 128. Okay, that's legally what I can get with this scale.
Oh, well, the maximum is $9.99.
Okay, and that's a problem, right? I know that this isn't a real value. That's not a value that this scale can have. So there's something going on that I need to go through and check, okay? And so when we're going through and we're doing screening, always want to look at this in terms of looking at the plausibility of your scores. I know that the max score I can have on this is 128. That's way above, right? Now, what I know from the way I code my own data is that 999 is used to indicate missing data, or someone didn't fill anything out. So I'm guessing what's probably happening is I've got 999 as a missing data code in here. Now, if I go back to my data, to my file, and I hit variable view in this missing, if I go to, I put 999 as a missing value, and I hit OK, what's going to happen is that tells SPSS that 999 means that data is missing. Okay, and if I go back through and I rerun this, now I see, once. Why did that not? Oh, that was the wrong one. That was a Z-score. Okay, here we go. Get rid of that. Right now, if I run this, now I see that, okay, now my scores run from 0 to 99. Okay, because I went through and I specified that. People see what I did there in that program, just so that I'm telling the program that 999 means a missing value. Okay. But what I'm going to do is I'm going to go through and I'll go back to my IIP total, sort ascending again. And if I go down, I see, oh, case 414 has a missing score for this. I've got scores for some of my subscales, but I've got a missing score for that total. So that's going to be another case that I'm missing, right? So I'm going to go back through. I'm going to say case 414 missing IP 32. Just so I document that so I can remember what's going on with my data, okay? And then I'm going to go through and I'm going to get rid of that too. All right? So now I'm going to go through and I'm going to get rid of, these are just z-scores that I've calculated up to this point. So now I've gone through and I've made sure that the data that I'm going to be using is data that has sort of proper values for my IIP total. I've got 334 people in my sample, okay? And so then if I go back through and re-highlight my descriptives and run those, all right, now I see my descriptives here. So I've got 334 people, minimum value of 0, max value of 99. My mean for the sample, 39.85. Standard deviation about 20. And then I'm going to look at my skew and my kurtosis. Okay. Allie, how do I feel about my skew and kurtosis values here?
I'm trying to remember something's like let's see.
Oh,
I know.
Ari's got COVID.
What?
Oh, no, I said Ari's got COVID. She was coughing. I'm sorry. That's not funny. Ari doesn't have COVID.
Yeah, I can't remember what the skewness or I can't find that in my notes right now.
Okay. So with skew and kurtosis, right? General rule of thumb is if skew and kurtosis values are less than 2, you'll get a pass on that, right? Like, okay, it's sort of would say it doesn't have those problematic violations of normality, right? But remember that these are just rules of thumb. That it doesn't mean that like my data are normal so long as that my skew and kurtosis values don't fall below 2. It's just standard practice to kind of sort of look at it and sort of say, okay, well, it's not, probably doesn't have terribly problematic distributions, right? Also remember that, are we concerned, Robert, about the actual distribution of our outcome? Is that an assumption in our single sample test?
Sorry, can you repeat the question?
Yeah. Does a single sample t-test require my observed data to be normal?
No.
No.
Looking at me, right?
Yeah. It's my sampling distribution. My sampling distribution needs to be normal, right? So I've got 334 people. How fast is that mean? I mean, that's a huge sample, right? The distribution of my sample means is going to become very, very normal very quickly with a sample of this size, right? So I'm feeling pretty good about not having too much of a problem with my distribution. But what I want to do is I still want to go through and take a look and see graphically what's going on. So if I look at my skew and my kurtosis, these are values which are falling within range that probably wouldn't raise any red flags or cause concern, but it's always good to go through and take a look at your distributions and see what's going on. Okay. So what I'm going to do is here I'm going through. You can do this a couple of different ways. I can go to graphs. I go to chart builder. And I could say that I want a histogram. So there I'm going to take my histogram and pull it up into the top. And I want my IIP32 score. I'm going to pull that down here. And we'll just run a simple graph for this. I'm going to hit paste. Okay, that's going to throw that into my syntax file. Then what I can...
Sorry, Josh.
Yep.
Can I ask, what happens when you click OK instead of paste?
Oh, it'll just pop it up in your outcome window.
Oh, but paste puts it in your syntax.
Paste puts it in my syntax file. So if I hit paste, so this is just so I just have a record of it here.
Yep. Okay.
Okay. And so same thing if I go to graphs, chart builder, and let's say I want a box plot. And so if I go and I sort of select this one here and pull this up, and my IIP32 is already here, and I go ahead and I hit paste here, That's going to put my my box plot right up here. Okay, and so what this is going to do is it's going to give me a plot of a histogram of my outcome, and then also a box and whisker plot. Okay, so let's go through and take a look at our histogram first. So we run that. Brittany, what are you thinking about this histogram here?
Distribution wise?
Yeah.
Looks almost normal, I guess you could say. It's a little off, but I mean, if you looked at it, I would say it's pretty close to normal.
Yeah. Anybody have any concerns with this distribution here? No, looks pretty good, right? We've got someone who's kind of fallen a little bit high, who's separated from the higher end of the distribution, but that's fine. With a sample of 334, we're almost always going to have people who have sort of inordinately high or low scores here. 0 is the low end. You can't get any lower than 0, so it's kind of truncated. But we've got some people who are experiencing a large amount of difficulty, right? Which makes some sense given that we're working with people who have experienced some sort of traumatic event. We would expect at least some people to be struggling with stuff. If we look at my skew and kurtosis, it says I got a very, very slight positive skew and some negative kurtosis. Natalie, you remember what negative kurtosis looks like?
I was just trying to remember. Trying to remember. Were you the one who was talking about like the kangaroo trick?
Yeah. Yeah.
That was for kurtosis, right?
Yeah. Yeah.
So then, like, it's more narrow.
Okay, so that would be positive kurtosis. Here we've got negative kurtosis, right? And remember, negative kurtosis is kind of that square distribution, kind of that mounded kind of thing. It's kind of got a flat peak and heavy shoulders, and we're kind of seeing that here in this distribution. So if I look up and my kurtosis here is negative 0.61, you can kind of see that this is kind of humped. It doesn't have sort of tails that really spread out, right? But all in all, not too concerned about this. This is looking pretty good, right? I would identify this as no serious violations of normality, sort of based on these data. I would say you could call this, say it's relatively symmetrical, right? I could say that this is unremarkable, sort of fine. I mean, it's okay. You've got one value hanging out here that's a little bit detached from the rest of the distribution, but depending on how I set up my histogram, then that's going to change. So Robert and Allie, when you're running histograms in Stata, you actually have to tell it how many bins it's going to put in, and depending on what kind of number, it's going to change what the shape looks like. And that's really the drawback of histograms, is depending on how I bin that data, it can really start to change what the shape looks like. And so this is one of the reasons why if I go through and I run my box plot, remember that box plots are box plots. Box plots follow a set of rules. And so your box plot, I mean sort of the surface level stuff is going to change. But Riley, what's the midline of my box plot represent?
The mean?
Close. Median. There we go. Remember, your box plot is a median-based graph. So I've got a median value here. I've got my third quartile, my first quartile, right? Here's my middle 50. 50% of the scores fall within the bounds of the box. And then, Robert, what is, in this graph, what does the upper bound of my whisker represent?
That would represent the confidence interval. Or wait. No, that's just a maximum value. So
there you go, max value. And what about the lower bound? The lower,
minimum.
That's the minimum, right? Now, if we had scores that were falling outside of 1.5 times the inner quartile range, then we'd start to get points and asterisks along the way. But here we don't have any points or asterisks. So my upper whisker and my lower whisker are just the upper and lower, the max and the min in this. Okay. And again, Robert, if I'm looking at this box plot, what are you thinking about this box plot?
The interquartile range is relatively normal, which is kind of consistent with what we saw based on the data in the previous graph.
Yeah.
We see that the. Were you going to say something?
No, I was going to say, any concerns with this?
No, I wouldn't say so. I don't think so.
Yep. So this is looking pretty good, right? What I've got is so based on my skew and kurtosis values, I've had, it looks like my data are falling within sort of reasonable bounds, right? Stuff, particularly given a sample of this size, nothing that we would be worried about in terms of our distributional estimates here. If I go through and I run my histogram, looking okay. I have a value that's kind of hanging out there at the top, but it doesn't look like it's too big of an issue. Natalie, is this person right here going to, in a sample of 334, is this person going to drag the mean out towards the top?
Probably not a ton.
No, it's not going to be fine, right? And again, we would expect, if again we're looking at trauma survivors interested in interpersonal difficulties, some of these individuals are probably going to have some symptoms, right, that may lead to interpersonal difficulties. So I would expect some folks to be hanging out there in the top. With a sample of this size, that's not going to be a problem in terms of how far it's out or things along those lines. Box plot is all looking good. No extreme values falling beyond 1.5 times the interquartile range. So all in all, I'm feeling pretty good about this. Okay, so I'm comfortable. I'm thinking, okay, looks like at least these data are at least reasonable in terms of moving forward with this analysis. What's the last thing that I might want to go through and take a look at before I just jump into my actual running my actual analysis? What I might want to do is I might want to go through and take a look at, remember in my data set, I had told SPSS to save z-scores, okay? What I might want to do is go through and take a look at my z-scores, just so when I tell people I don't really have any evidence of extreme values, I can give them a number for that kind of means something. So it's not just, oh, people have to trust me, okay? So if I go back up to Analyze, and I go to Descriptives, go down to Descriptives here, and I remove IAP32 total and put my z-score, okay? So this is my z-score of IAP32 total. I'm going to cut off standardized values because I don't need to calculate z-scores on my z-scores. That's not a useful thing. And under options, I don't need skew and kurtosis because I already know skew and kurtosis, my z distribution are going to be the same as my observed distribution because that's not going to change, right? So I'm going to go through here, then I'm going to go hit paste. And I'll see in my syntax file, if I go through just to keep this, say, distributional graphs, okay, and then I say I'm looking for extreme values here. So if I go through and I run z-scores on this, all right, Erica, what am I seeing here in terms of my z-scores?
The minimum and maximum.
Yeah. So what is my minimum z-score here?
Negative 1.98.
1.98, right? Telling me that the lowest scores in my distribution are about just a little under 2 standard deviations below the mean. Okay. And what is my upper bound, or what's my maximum z-score?
2.94.
2.94, telling me that at most my highest score is close to 3 standard deviations from the mean. Okay. Now, what we want to call an extreme score sort of depends on sort of how we want to define it. With large samples, usually we would use kind of a general benchmark that's associated with a p-value of, say, 0.001, right, for a large sample. Because with the large samples, I expect to start to get things that are pretty far out there, right? The larger my sample, the more of that variability I'm capturing, right? So generally what you'll see is people say a z-score for these large samples of 3.29 as indicating sort of a rough way to gauge sort of extreme values. Now, again, we always want to use these carefully and not as hard rules of thumb. But for a sample of this size, I'm saying that these z-scores are falling within sort of reasonable what we would expect from a large sample. Okay. So again, remember when we're talking about z-scores are telling me number of standard deviations above or below the mean. Okay. And so I know as I get 1 standard deviation above and below the mean, are those very extreme values? Not really. Those are kind of falling in the middle of the distribution. If I get 2 standard deviations, that's starting to get pretty extreme. 3, those are pretty rare values, right? But with a big sample, we're probably going to get those, right? Now, if I were to have a z-score of, say, 4 or 5, I might be concerned and want to go back through and take a look and see where that was falling. But this is just giving us a standard metric to tell us, sort of in standardized units, how far are scores falling in this distribution. Okay. Questions about sort of the screening that we've done here? All right. In this handout, it's just going to work you through everything that we did along with the syntax. Now, writing this up would be a pain, but if you're going through and hitting paste, you've got this all sort of set up here that you can then file and save, and you just pull that back up, and it lets you know what you've gone through and done, which is really handy. So all in all, Ari, how are we feeling about our underlying assumptions going into our statistical test, at least in terms of our formal assumptions here?
Pretty good.
Yeah, we're feeling pretty good about this, right? We've gone through, really for a single sample t, only thing we need to worry about is the distribution of our outcome. And remembering that our actual assumption involves the distribution of the sample means, not the actual observed data itself. With a sample of 334, feeling really good about the robustness of this, right? My data could actually look pretty nasty in terms of my outcome. It could be terribly skewed, and I'd still probably feel okay with a sample of this size, right? But it's always good to go through, take a look, see what my data are doing so that I know what's happening with these scores, that it starts to inform sort of my understanding of the behavior and how I'm measuring it and capturing it. So always want to go through and take a look at this stuff before we jump into our actual analyses. Okay. Questions on anything here? Okay, cool. Let's do this. Let's take a break. Let's come back at a little before 4:20, and we'll jump through in the actual analysis of this in SPSS. Sound good? Okay, cool. I'll let you know, all you clinical folks, my wife tells me that you like her better than you like me. But then she's like, you give them 2 breaks? I was like, yeah, I give them 2 breaks because I care about people. And I want to try and overwhelm people with stuff. So I don't know what sort of task, sort of chain gang she's running with you guys outside. How you move stuff around, but not here. 2 breaks. 2 breaks on Zoom. That's my platform.
You might give more breaks, but she gives nice benefits, so.
Well, I can't show up to your house and give you, like, there's nothing, you know what? It's a free country. Nothing stopping you from doing whatever you want to do in sort of your own time, sort of back there. So, all right. So don't try and don't try and put that on me, Riley. Nice try. Nice try. What's
You're
that?
the only professor who gives 2 breaks.
I'm the only professor who gives 2 breaks?
All right, wrong. Experimental with Ben and Karen. Karen
Okay.
only gives 1. Yeah. You are a nice dude.
See there?
Because, yeah, look at you.
Right? The lengths I go, to make sure that you're sort of comfortable in this whole situation. All right. Speaking comfortable in this whole situation, how are people feeling about sort of going through this initial screening and stuff like that? Kind of getting a headspace for this? Okay. One thing I forgot to add, I just added it over the break. In terms of, so we went through and ran this screening and things were looking pretty good. What I'll have you all do is put together a write-up. Okay. And so what I've done is I've posted this as kind of a write-up of the screening for this single samples T. Okay. And so we're screening going to start with missing values. Here we had missing values for about 70 cases. So we're reporting that. Accuracy and plausibility of scores. We're saying we've got an invalid score, 999 for case 414, making sure that we indicate that. Going to say cases with missing and implausible values removed, 334 for our reduced set. So just kind of talking about what we did to get down to our working set. Going to describe our univariate distributions, skew and kurtosis, not finding any problems there. Histogram, symmetrical, one case falling slightly away from the continuous distribution. Box plot, unremarkable, no values falling 1.5 times in a quartile range. Univariate outliers, looking good. Here I'm saying all z are less than or equal to absolute value of 2.94. That just says no values in my set were exceeded sort of absolute value of 2.94, so plus or minus, right? So make sure we've got that covered. And then what we're going to do is put together recommendations. Here, when I'm asking you to do these, you start doing these in set 4. So I want you to act as you're putting on the consultant hat. Someone said, hey, can we come in and can we run a single sample t-test? And you're saying, okay, based on what I'm seeing, this is what my recommendations would be, right? So we say we do note substantial missingness, right? Over 17% of cases. So there's a lot of missing data here. We want to account for that. Invalid score in 414 likely meant as a marker for missing values, but we want to go through and check that. Little evidence of outliers or extreme values, problematic violations of normality, right? So say missing is concerning, however, assuming that we've covered that, recommend proceeding with the analyses. So you're just kind of taking all the stuff that we did for that screening and recognizing we're just not doing it for the hey-ho heck of it. What we're going to do is pull this together and sort of put together some recommendation for, is it recommended to move forward, or are there things that we should be concerned about? Okay.
Is this going to be, did you say you're going to upload this to the files?
Yep, it is. It's up there right now. Okay. So, and I've got one for your independent sample, your paired sample. We're just going to use this as a format. And again, I don't give you many things that are like, oh, use this as a template. Don't get creative. You don't need to be a hero. Come up with your own. Like, just use this in terms of going through and talking about sort of how we're putting together this screening information. Okay, don't cut and paste, because you need to change it around because the screening stuff will change depending on the problem. But in terms of thinking about missing values, accuracy, plausibility, univariate distributions, outliers, recommendations, this is how I want you to be thinking about this stuff. Okay, cool. All right, so what we want to do then is jump into our analyses. So and this is what happens, we spend all bunch of time going through and screening stuff. Now we can actually get into running the analyses that we want to do. And the analyses we want to do takes about all of like 2 seconds to go through and run an SPSS. So for what we're going to do is we're going to go analyze. We're going to go to compare means. We're going to go one sample t-test. Click on that. And we're going to say, I want to take a look at IIP 32. And here, what I need to do is I need to put in my test value. For this problem, someone remind me what my test value is. What's our value under the null for this problem?
25?
25. Okay. Because that's what we're testing. That's our normative value, right? The mean value in the normative population for the IIP 32 is going to be 25. Okay. So that's our null value. And then if we go to options, we can see that we can start to change the level of estimation for your confidence interval if you want. We're not going to fool around with that. We don't need to change that. So I'm going to hit paste here. And then if we go to your syntax file, you see your t-test here. So I'm going to go single sample t-test. So I know what's happening. Okay. Go through, highlight that, run this, and then take a look at my outcome. And here we go. All right. So, Rachel, what are we seeing in terms of my output for my single sample t-test here?
Well, on the top you have your n, your mean, your standard deviation, and standard error of the mean.
Okay.
And you have the test statistic and stuff in the second.
Okay. So holding on to this. Always, always, always. So we've gone through and done a bunch of scoring, but never overlook this sample statistics. You want to go through and take a look at this and make sure that it squares with everything that you think you're doing, right? I should have, so I'm saying that this test is running on 334 people. Is that the number of people I think should be running in this? Because if it's not, then I screwed something up. I need to go back through and take a look, right? And just making sure that this is working out okay. All right. But now, Rachel, continue to help me out here. What inferences are we, what are we pulling from the output here?
Well, you probably want the t-statistic.
Uh-huh. And so my t-statistic is 13.5 with 330 degrees of freedom. Is this a big t-statistic or is this a small t-statistic?
I'm not gonna lie to you, I don't remember if
Yeah.
it's big or small.
Yeah.
So I don't think it's super big, but
Okay. Any differing opinions from this is super big? This is huge, right? And if we think about that t-test, right? If we think about as our samples get larger and larger, what our cutoff value or critical value for or for alpha 0.05, it's going to be 1.96. And for 0.01, it's 2.58. And for 0.001, 3.29 in terms of like Z values. So a t statistic of 13 is massive. It's really, really huge, right? And so if we go through and we take a look, we see our p-value here is less than 0.001. We never would put p equals 0.000 because it's never, our p-value is never exactly 0. In sort of standard terms, we would just point that, say that p less than 0.001, but I'm going to encourage you to report this a little bit differently. We'll get to that in a moment. The mean difference, so the deviation between the value that I've observed for IIP and these individuals with difficulties is 14.85 relative to the normative sample, and then my confidence bounds here. Robert, can you give me an interpretation of these confidence bounds?
That's the range of plausible values that we find based on the data we collected.
Right. So based on the data that we've collected, I would expect that the true value or the true mean value for IAP scores in trauma-exposed undergraduates are going to vary somewhere between 12.69 to 17.01 points higher than the normative population, with my sort of point estimate being about 14.9, about 15 points higher. Okay. People see that? Okay. So, and this is it. This is all that there is to this. I mean, that happened like a snap. The big thing was going through and screening the data and taking a look and saying, hey, can we move forward with this? But once we get to the actual test, easy peasy, super fast. Okay. So if we go through and take a look, right? So to run my single sample test in SPSS, again, using the pull down menu, so that you can go through and sort of, we did this analyze, compare means, one sample t-test, or you can just go through, if I wanted to, and this is where syntax starts to get helpful. If I wanted to say, look at, oops, not that. If I say wanted to look at, run a t-test for, let's say, this domineering controlling IAP DOM. Okay, I'm just going to copy that. Yeah. All right. Let's say that I wanted to run this for a different variable. I can just copy and paste that. And I want to go IAP DOM. Whoops. And I want my test value to be 28, let's say. You can go through and I can run that, right? And so this is part of the reason, one, in terms of documentation, your syntax file is going to be nice to keep track of that. But then two, it starts to become much easier to go through than sort of run through all your pull down menus and stuff like that. Once you get comfortable and you know what these are, you can just cut and paste and sort of move around and stuff like that. It sort of makes it a little bit more efficient. Okay. So either way, whether we run it through the pull down or run it through syntax, go through and run it. This is what we get. My t-test, I get my one sample statistics. My test value here is 25. My t-statistic, my degrees of freedom, mean difference, this is my point estimate. Here's my upper and lower bound. Everything I need here. Okay. Ali and Robert, in Stata, this is Stata's interface here. Running a single sample test is easy. Down here in the command, you just put t-test, put your variable, whatever your outcome is, equals whatever your test variable is. That's it. That'll just pop it out there for you. And then, so the output looks, I don't guess I got to have an output variable in there, but output will look similar. And you can take a look at a handout with that. Okay. So here, if I'm going through and taking a look. So first thing I wanted to do is I said, want to list out the null hypotheses in a sentence, right? I'm going to say the mean score for IAP 32 interpersonal difficulties in the larger population of undergraduate survivors is 25. Okay, so notice here what I'm doing is I'm identifying my measure, I'm identifying the population, sort of everything like that, kind of pulling that in. And sort of what I'm saying is my null hypothesis is that the data that I've got were generated from a population having a mean value on this measure of 25 that's equal to the general population or normative population. Okay, here I've got my, in statistical notation, mean of IAP is 25, mean of IAP isn't 25. Got my confidence interval. Okay, got my test statistic with my degrees of freedom, and then my p-value. Okay, here what we would normally see is p less than 0.001. Okay, but if I actually look at this p-value and using exponential notation, okay, everybody's seen exponential notation before, right? Or scientific notation, right? People know what this sort of means, looks like. Okay, the reason I like this, and so I've sort of come to like this more in terms of p-value. Someone, Rachel, I saw you nodding your head. Sorry, I keep picking on you. But you said sort of scientific notation. How small of a number is this?
Really small?
Yeah, extremely small, right? This is 0.31 zeros and then some stuff on the end. That's incredibly small. Rachel, is that a different number than p equals 0.0009?
Yes.
Yeah, a much different number, right? And so if we're thinking about interpreting p as a continuous measure of evidence against the null hypotheses, p equals 9.5 times 10 to the negative 32nd is a very, very different number than p equals 0.001, right? And so in terms of talking about and sort of conveying information about how much these data functionally based on the p-value, assuming that we're good on all of our assumptions, these data are completely incompatible, in no way, almost impossible, assuming a population value of 25. Like functionally, these data can't exist, right? If that were true. So incredibly strong evidence against the null hypothesis. Okay. So, and we'll talk about, I'll talk a little bit more about sort of how to get that value for reporting. Also wanted to report an effect size. Calculate an effect size of 74 or 0.74. This is easy peasy. Okay. So remember, my effect size is just going to be the observed difference I found divided by the standard deviation. So if I go difference that I observed here, oops, not that one, that's not what I'm looking for. Okay, my observed difference, 14.85, divide that by my standard deviation is 20.092. Whoops, dang it. 14.85 divided by 20.092, 0.74, okay? And so what I'm going to say is basically what this data is saying is that the observed mean that I've found my sample data, the mean IAP score in this sample is about 3/4 of a standard deviation above what we would see expect in the normal population. Okay, and if we think about 3/4 of a standard deviation in terms of effect size, if we think back to those benchmarks, that's sort of approaching that large effect. So we're seeing that we've got sort of a reasonably large effect. So we got 3/4 of a standard deviation increase over the expected value under the null based on these hypotheses. Okay, so anytime you see a D, you should be thinking about these in terms of Z-scores, interpreting these in standard deviation units. Okay. Now, what we also want to do is calculate S values and Bayes factor values, right? Now, we're going to have you do these. Oh, I don't know that this calculator will do it. Okay, there we go. I can do this. Okay, so what I could do is for my S value, right? S value is going to be the natural log of P divided by the natural log of 2. So if you've got your scientific calculator, you could take, oops, clear, 2, or excuse me, let's say, for example, that I had a P value of 0.05, right? So I go 0.05 natural log divided by 2 natural log equals is going to give me, taking the absolute value here, so it's going to be 4.3. Okay, so give you an S value of 4. So that's fine to do here. Okay, but remember that for this problem, my p-value is crazy small, right? And so how did I get that? Well, what I did is I used a little bit of magic that I will have you also engage in. Close. All right. So what I've got, and we'll do this a lot, is calculate, so to go through and put together Excel sheets that will help streamline your analyses. So here, if I go through and I take a look in SPSS, right, and it gives me a p-value just zeros, right? Well, I know it's not 0. I would point 0.001. But if I go through and I double click that cell, I get a value of 1.86 to the negative 33rd. Okay. And if I go through and I double click that and I copy and paste this into this Excel sheet that I've created, and I paste that there, it's giving me 1.866 to the negative 33. So it's giving this to me in scientific notation here. Okay. Also, what I've done is I've set this up so that it will now start reading me Bayes factor or my S value and Bayes factor here. And so if I go through and I punch that in, so I could do it this way, or I've also set up this calculator so I could go 13.508 with 333 degrees of freedom. Let's see, that's 13 point. Okay, it looks like I didn't quite. .545. Looks like my p-value on there was a little off. Okay, I need to adjust that. But basically, what it's given me is an S value here, my Bayes factor, given it in scientific notation here, right? That then I can then punch into my output. Okay. And I'll show you how to do that. We'll work on getting those calculators set up, but super easy because then you've got it. And then whether or not I'm working with a p-value or I'm working with a t-value, I can just punch whatever I've got in here, and then it's just going to calculate it for me. So I don't have to worry about running things by hand and making mistakes and things like that. Okay. So my S value for this p-value here is 103. So I would say for these data, evidence against the null hypothesis of a population mean of 25 on the IAP 32 in undergraduate trauma survivors is similar to that of observing 103 consecutive heads in tosses of a hypothesized fair coin. Okay, Erica, you gave me a little bit of a more of a leeway in terms of how much you trust me on my hypothesized fair coin. What if I got 103 consecutive heads? Would you think that my coin was fair? No, it's impossible. It's functionally impossible for that to happen, right? So using this S value to start to augment like how inconsistent these data are with the null hypotheses. Functionally, from all practical standpoint, these data could not occur assuming that they were pulled from a random representative sample of a population having mean equal 25. Okay, same thing with your Bayes factor. Yeah, 5.45 times 10 to the 28th. Is that a big number? It's a massive number, right? That's huge, 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 right? And so really we would say the data-based odds for the alternative hypotheses of a population mean other than 25 are, at most, it's a higher end, 5.45 times 10 to the 28 times that of equal scores across undergraduate survivors and members of the general public, okay? So looking at this, right, it's easy to say if we're looking at our output, right, it's easy to look at this and say, oh, yeah, I've got p less than 0.001. Okay, so I have an effect, right? But if we go through and we take a look at, sort of actually look at the p-value and look at the S and look at the Bayes factor, how confident are we that undergraduate trauma survivors likely have a higher score on this interpersonal difficulties measure than, say, the general public? It's almost a certainty, right, based on the data that we've had. Now, assuming that we've got a reasonable sample, right, assuming that my sample of undergraduate trauma survivors are representative of undergraduate trauma survivors in general, but this isn't just like kind of some evidence. This is huge evidence, right? Questions about what we've done here, or how we've gone through and interpreted this stuff?
So the interpretation, let me look. So the mean difference, no, our test statistic is 13, right? Is that the number that falls between the plausible bounds of our confidence interval?
No, so this is our T statistic, right? And if we go through and we wanted to see if we wanted to take a sort of a traditional approach. So what I've got here is a critical t-value calculated. So this is Daniel Soper. This is a sort of thing. So with 333 degrees of freedom at alpha 0.05, my critical value is 1.97. So I'm using functionally using a z distribution at this point, right? So what I would do if I was doing the traditional hypothesis stuff that you all are working on right now, what I would do is I would lay out my curve, Brittany, and I would say, okay, my critical value, so a t-score of 1.97 or higher sort of marks sort of my upper and lower bounds. And I got a t-score of 13.5. That's way out there. Way out there. Right.
Okay.
So
when we, sorry.
No, go for it.
Well, when we interpret this, I guess maybe I just don't know what this data mean. Like, it doesn't make sense to me because I've never used it. So when we interpret this, we're saying that our population of undergraduates does not have a mean score of 25, but so what does this mean? What does their 13 score mean? Like, they have.
Look at that. Okay. So this is an example, and this I think is good. Now, I've never had such a situation before where almost all of the clinical cohort are trauma folks, right? And so a lot of the data I'm using is trauma data just because it's the data that I have. But I think having to work with data that's not exactly stuff that you work with is kind of good because it forces you to actually think about, okay, what are we measuring? What does this stuff mean, right? So if I wanted to pull together all the stuff that we've gone through up to this point and kind of turn it into sort of some sort of meaningful sort of interpretation, this is what I might write up for an assignment, right? So we're saying single sample t-test was used to compare interpersonal difficulties reported in trauma-exposed undergraduates against normative scores from adults in the general population. Okay, null hypothesis posits no difference in interpersonal difficulties in undergraduate survivors relative to members of the general population. Okay, so what I've done here is I've just set up for the purposes of this, just to say, okay, this is what we're doing. We're saying this is what interpersonal difficulties look like in the general population. Okay, what I've got is I'm interested in a population that's not the general population. It's undergraduate trauma survivors. How do interpersonal difficulties in undergraduate trauma survivors compare against sort of everybody, right? And so my null hypothesis, because I know what the normative score for this is I'm going to say my null hypothesis is that undergraduate trauma survivors have equal levels of interpersonal difficulties as assessed through the IAP as the normal population, okay? Then we say data were screened prior to analyses, concordance, sort of blah, blah, blah. Sort of going through some of the screening stuff. You can go through, take a look at that, right? Then we say trauma-exposed students in the current study, evidence in IAP total, M equals 39.9 with a standard deviation of about 20, okay? So what I'm doing is I'm communicating to you, okay, this is the point estimate, right? So Robert, what is my best guess for the mean or the average IAP total score in undergraduate trauma survivors?
Based on the study?
Yeah.
39.9.
Yeah. So my best guess for what the true average IAP score in undergraduate trauma survivors is about 40. Okay. And here's my standard deviation. suggesting 3/4 of a standard deviation increase in interpersonal difficulties relative to scores from the general population. So what I've just done is I've worked in my effect size here, right? I'm saying this is my point estimate, and my point estimate is about 3/4 of a standard deviation above what I would expect based on sort of the normative population, okay? Then we say population differences across trauma-exposed students and normative adults ranging from 12.7 to 17 found to be compatible with responses to this study. Brittany, what am I talking about here?
The values that you're, well, I guess the population differences across your students and your adults.
Yeah.
The range would be
And where did I get those values from?
from your confidence.
From my confidence interval, right? So I'm going through and pulling those in, right? And so I'm saying my best guess is I'm about 3/4 of a standard deviation above the mean, but anything from about 12.7 to about 17 points above sort of reference population is about what I'm expecting from undergraduate trauma survivors. And you can say a single sample t-test identified the data as highly incompatible with the null model specifying a population average of 25 in trauma-exposed undergraduates, right? And then I got my t-statistic, my p-value, my s, my Bayes factor. I don't need to go through and sort of, I'm just saying these data are functionally impossible, assuming sort of that I've done everything right. These data cannot occur in a sample of this size from a population with a mean value of 25. Okay, so I've gone through here. I've set it up. Here I've talked about my screening. Here I've gone through and talked about my results, and now kind of pulling it all together. Results of these analyses provided support for moderate to large elevations in interpersonal difficulties among trauma-exposed undergraduates, while compelling missingness in the larger set introduces the possibility of bias, right? So I'm going back to, hey, I found in that data I was missing a whole lot of folks. So I want to take that into consideration, right? I would say also it's important to note that the participants in this study were substantially younger, more predominantly female, and more highly educated than respondents included in the normative sample. Therefore, unable to determine from this study whether elevations are a function of trauma or some other factor, right? So what I'm trying to do here, Brittany, is go through and say, okay, not just interpret the data to say, yeah, there's a significant effect, right? That's useless and doesn't tell me anything, right? What I've done here is trying to incorporate all the things that we've talked about. So thinking about effect sizes, S values and Bayes factor to try and talk about strength of evidence, confidence bounds, so we can say what's the upper and lower limit on the difference, and then thinking about what's going on with my sample relative to what I'm trying to do, and saying, yeah, I do have massive evidence of higher scores sort of in this population relative to the general sample of adults, the general population, but there's other things that could go into, so my sample is different in a lot of characteristics, not just because of trauma. So things are looking promising, but would want to go through and take into consideration that, I don't know, maybe it's just that these are younger. Maybe younger people have higher levels of interpersonal difficulties because my life's filled with drama and I have fluctuating relationships that don't occur if I'm sort of old and stale like me, right? Or maybe there's all sorts of other things that could go in. So yes, these data are consistent with sort of elevated levels of interpersonal difficulties, but some other stuff that I need to be thinking about. Questions about this?
Yes.
Yeah.
So the 12.7 to 17, I'm just trying to understand. The number we found, like the 40, the 39.9, is way above those bounds.
Mm-hmm.
Therefore, that's why it's inconsistent with the null hypothesis, right?
Yeah. So, and this is
Okay.
this is something that's a little bit different, right? And I think you pointed on a good thing. That confidence bound, what does that confidence bound correspond to, Brittany? What's the outcome there?
Our population, right?
Right.
Our population, not our sample.
Right. Well,
Okay.
but what it's doing is SPSS is giving me the confidence interval of the difference. Okay. So the difference between my actual observed mean and my test value is 14.85. and it's saying the lower and upper bound difference of that is anywhere from 12.7 to 17.0. Okay. Now, if I were to open up in Stata single sample T, Stata presents this a little bit differently. What does my 95% confidence interval correspond to here, Brittany?
95% confidence. The two, like the 37 and the 42.
Yeah.
Okay. Oh, it's different.
Yeah. And so what is this a confidence interval for?
Population mean or your
Yeah.
sample mean?
Well,
Population mean?
well, there's my point estimate here, right? So what Stata is doing is it's giving me a confidence bound around my estimated mean, right? So it's saying that my mean is anywhere, sort of the actual, the mean score, my best guess for the actual score in the larger population of trauma-exposed undergraduates is 39.9.
Yeah.
But based on my data, it could be anywhere from 37.7 to 42.
Well, that makes more sense to
Right.
me. Why does SPSS do this?
It's just the way it presents it. Are they different things?
No, it's just telling you like.
Yeah, it's just providing a different metric, right? So if I take here, if I take 12.69 and let's do this. If I go 17.01 and I add my point estimate of 39.85, you get 56.86. Oh, that didn't work out.
It makes sense to me though, because like the mean difference is the difference between what your population mean and your sample mean.
Yeah.
And it's giving you the values that it could either be 12.6 lower or 17 higher. It makes sense to me. Like
Okay.
The mean difference. Yeah.
Okay.
Shouldn't you add it to the test value instead of like 25? 17 plus. That'll give you around 42, right? Because it's the mean difference from what you would expect it to be.
No, because my test value is just the value under the null.
Yeah, isn't that what the mean difference is? Like the mean difference from the null?
Yeah, this is the mean difference from the. But this is just cripes. I need to go back through and take a look at this. So this is just a sort of confidence interval around your estimate, right? And then here what we're doing is the confidence interval around the mean difference.
But I think what Rachel's saying is, like, if you add 12.69 to 25, you get 37, which is what Stata's saying.
12.69.
That makes sense to me, Rachel and Riley.
Plus 25, yeah.
That's giving me 37 point. Oh, yeah. Yeah, exactly what you're saying. All right, I'm having a hard time thinking about why this makes sense. It doesn't make sense to me right now. I know it does. I have to think about this. Okay. Rachel's smarter than me. You all are smarter than me right now. But let me think about this because I want to go through. It just is sort of so State is doing a little bit different thing than here. But just the thing that I think to think about is remember that always with this stuff, we always want to make sure that we know exactly what our values mean, what they correspond to, and whether or not they make sense. Let me go through and check on that. You're actually right. You're absolutely right. Your math works out. I just need to go back through and wrap my head around this when I have a moment to sort of think. See what you guys did? You flipped the script on me. Now all of a sudden, who's asking the questions on the spot? And so, nice work. Okay. questions about where we're at right now? So, I mean, we're moving through this a little more slowly than what we would have on the syllabus, but that's fine. I would much rather have you all have a strong understanding of this and sort of working on this than just trying to rush through and have people confused. These mean-based tests are going to be the foundation for almost everything else we're going to do for the rest of the semester. So just want to make sure that people are feeling pretty confident with this stuff. Does this sound all right? Okay. So based on what we've got right now, it looks like set 4, you got set 3 that's due this Friday. But set 4 obviously isn't going to be due next Friday. Right now we're looking at maybe the 23rd if we get all the way through this. So just in terms of planning ahead, so you kind of know where things are at. So, and it's always nice to have a little bit of a hot break in between two of these sets. What I'll do is I'll get this set posted early. So you guys, this next one, this t-test one, this will be a bigger one, right? You want to get started early. You're going to be working with actual data. You're going to be working with actual statistical analyses. You're going to do screenings and stuff like that. This is going to be a level up from what we've done before, so make sure to get at it early, but you're going to have plenty of time to sort of slowly pick at this and move forward, okay? All right, questions?
The midterm, I know we're at time. Are you going to tell us about that eventually, like what it's going to be like?
Yeah, I need to figure it out.
Okay.
I mean, normally what we would do is, it would be an in-class exam, which people hate. And I understand that, but I also think it's good for a number of reasons. But we obviously can't do that. So midterm will probably be some sort of take home that I'll put a time limit on, and that's just so that you can't spend an exorbitant amount of time sort of going through and doing stuff. And so we'll get to that when we get to that.
Yeah. Sorry,
but
well, not sorry, but like just
yeah. So I'll keep you informed so you kind of sort of know where that's going along, so we can be flexible with it. Sound good? Any other questions, comments, concerns? All right, you guys are crushing it. Like you're doing really, really well. Stick with it. Let me know if you have any questions, and I'll keep posting stuff to the website in terms of resources and stuff like that. If you want to use them, if you're confused, go through and take a look, try and put those videos together. If you're not, if you're feeling like you have a good handle on stuff, don't worry about it. We'll kind of just take it as on a case-by-case basis. Cool. All right, cool. You guys have a good evening, and we will catch you next week. All right, we'll see ya.